This video gives a very brief introduction to sockets. After this, you won't know how to use a socket really, but you will be able to actually create one and know which parameters the respective system call requires, what these parameters mean, what options there are, and which consequences certain options will have. Sockets are a really old interface coming originally from BSD. The libc socket documentation puts it nicely like this. A socket is a generalized inter-process communication channel. So basically, a socket lets processes talk to each other. Mostly, we think of this as processes that communicate over the internet. But there are various types of sockets, and not all are meant to let processes on different hosts communicate with each other. That is the generalized bit of that statement. There are sockets for all sorts of different communication. For example, there are sockets to talk to the kernel, to talk to local processes, and various others. Since we are working with Linux, where supposedly everything is a file, it should not come as a surprise that also sockets are represented by file descriptors. So the handle on a socket, as seen by the programmer, is simply an integer. We will see that operations you might know from files do work on sockets, but there are many system calls that only make sense for sockets, but not for files. That is simply because a network connection is sufficiently different from a file that different operations need to exist. For example, a file does not have a port number or an IP address. You also do not need to establish a connection over the network in order to read a file. But there are also things you can do on a file, but you cannot do with a TCP connection. That includes, for example, seeking on a TCP data stream. But we will get to all of this over time. Sometime in the very near future, once we have looked at all the bits and pieces of the socket API, you might think that it has an awkward feel to it here and there. There are certain things you need to provide to the API, which other high-level languages might not require, and there are a few nested structures that are sometimes cumbersome to use. But don't worry, overall, the complexity of sockets is manageable. When we look at where the socket API lies in the protocol stack, we see that it provides its interface to the application layer, of course, which means using sockets you can implement things like DNS, HTTP and the like. The problem is that you need to provide information that is not confined to the layer below, the transport layer, but also need to provide information regarding the network layer, in particular a destination IP address. Only then you can use the services provided by the protocol stack. Each layer below has a number of choices to pick from, depending on the requirements of the application. For example, at the transport layer, there are multiple protocols to choose from, such as TCP or UDP. On Linux, there are more choices such as SCTP or DCCP, but since they are far not as relevant as the former two, we will focus solely on TCP and UDP. Also at the network layer, there are two major choices, one being IPv4, the other one being IPv6. The goal of this course is to write code that is as IP version agnostic as possible, since we have run out of IPv4 addresses, but at the same time there is no global deployment of IPv6 yet, so we need to live with both for some time to come. So there are two important choices to make when creating a socket. The first, as already mentioned, is the choice of transport protocol. In this course we will limit the choice to either UDP or TCP. If your application needs reliable data transfer, which most applications need for obvious reasons, then your choice has already been made and TCP comes out as a winner. TCP has a number of other properties that make it a good choice too, such as in-order delivery, which means packets are reassembled in the order in which they were sent. Also, congestion control makes sure the network is not pushed into persistent congestion, and flow control makes sure the receiver is not overwhelmed with packets at a rate so that it cannot process them. It is a connection-oriented protocol, so expect some initial delay before data can be sent. UDP, on the other hand, does none of this, but UDP has its use cases. DNS, for example, uses UDP because usually it is just one packet containing the request and another one containing the response. A connection setup would be a bit much overhead, only adding delay but little benefit, because the application can just resubmit the request in case an answer does not arrive within some sensible time frame. The second choice is the address family. As we already said, these days the choice is usually not one or the other, but both. in case the host supports both. There are other choices which we will look at later on, but these two are the fundamental ones. At this point, we are ready to look at how a socket is created. The system call is called, well, socket. When the socket creation fails, -1 is returned and the error number is set, so you can look up why it failed. On success, a file descriptor is being returned. The system call has 3 parameters. The first is called domain. For us, this is the address family, typically IPv4 or IPv6, represented by AF-INET and AF-INET6 respectively. It really finds the domain which is used for communication. In the list below, there is, for example, AF-UNIX, which is used to enable processes on the same host to communicate, or AF-NetLink is used to talk to the kernel. Depending on the value of this first parameter, you can pick your second parameter, the socket type. If we pick a network socket as the domain, which means AF-INET or AF-INET6, we usually pick either TCP or UDP, which are represented by SOCStream and SOCDgram respectively. The name reflects that TCP implements a byte stream abstraction. That means there are no message boundaries in the data you hand over to TCP. UDP packets are usually called datagrams and TCP packets are called segments, so SOCDgram also gives the nature of the used transport protocol away. Other sockets, however, allow different choices as a type. For example, for the NetLink socket, only SOCRAW and SOCDgram are valid choices. The third parameter is called protocol. Many of the domain type combinations only support a single protocol. In that case, the protocol parameter is simply 0. Some combinations, however, support multiple protocols. If that is the case, the choice of protocol goes here. And that's really it for creating a socket. It's not doing much at this point, however. Once you are done with the socket and you want to release the file descriptor that the socket call has given you as its return value, you call close, passing that file descriptor as its sole argument. Again, -1 indicates an error and the error number is set, 0 signals success. All the interesting stuff happens in between calling those two functions, and what that is really depends on a number of things. In particular, you will be using different sets of system calls on a socket depending on which transport protocol has been chosen and on whether you are writing a client or a server. But we will get to that. Before we continue with the socket interface, this is a good time to introduce a tool which comes in quite handy when inspecting sockets, and that is SS, which provides all sorts of useful socket statistics. You might be familiar with its predecessor netstat. Here are a few useful command line switches of this tool. You can show all sockets using -A. That includes all listening and non-listening sockets. We have not talked about listening sockets yet, but it basically means server sockets. More on that later. If you are only interested in those, you can use -L. SS will also tell you which process the socket belongs to, which you can tell SS by using the -P switch. You can also limit the tool's output to only display sockets of a certain type. For example, you might only want to display TCP or UDP sockets. There are many other command line switches available. For starters, this is a good selection. We will be using more once we dig deeper into the socket API. At this point, we can already code a little. This is a good opportunity to write a small template that we can use for later assignments. Let's write a small program that creates a socket. Make that an IPv4 UDP socket, and after you created that socket, halt the program with getchar, so that the created socket stays alive and you can, maybe, inspect the socket with SS. When getchar returns, close the socket and exit the program. Also, create a makefile, just to get back into the habit. This exercise is intended for you to get familiar with the toolchain, in particular if you have not been programming C for a while. Also, you get to use the socket system call. You can play around with various combinations of the domain, type, and protocol parameters to see what happens. Also, you will start to use the first command line tool that might come in handy once you start developing production code. Happy coding!